In this video, we're going to answer some questions and work some example problems related to the enthalpy of chemical reactions. So let's get started. Define these terms, enthalpy and enthalpy of reaction. So enthalpy, the definition of enthalpy is equal to U plus PV. The internal energy at some moment plus the pressure times the volume at that same moment. That's enthalpy. The enthalpy of reaction is just the enthalpy change as a result of a chemical reaction, and you can find this by taking the total enthalpy of the products and subtracting the total enthalpy of the reactants. Note that the definition of enthalpy has nothing to do with like a constant pressure process or any specific kind of process. This is in complete general. Okay, under what condition is the heat of a reaction equal to the enthalpy change of the same reaction? So there is a case where the heat given off in a reaction is equal to the enthalpy change of that reaction. That's for a constant pressure process. But again, this definition of enthalpy has nothing to do with a constant pressure process. In writing thermochemical equations, why is it important to indicate the physical state, that is, gaseous, liquid, solid, or aqueous, of each substance? Because substances in different states have different enthalpies. And we just talked about how the enthalpy of a reaction is equal to the total enthalpy of the products minus the total enthalpy of the reactants. Well, that number is going to be different depending if you have one reactant or product in a certain state. So like aqueous, for example, if you go from the gaseous state to the aqueous state, there's an enthalpy of hydration, of being hydrated by water molecules. Explain the meaning of this thermochemical equation. 4 moles of NH3 gas plus 5 moles of O2 gas produces 4 moles of NO gas plus 6 moles of H2O gas. And the change in enthalpy, the enthalpy of this reaction, is negative 904 kilojoules per mole. Well, it doesn't tell us anything about whether or not this is a constant pressure process or constant volume. So in that case, if we're just thinking about this completely generally, what this delta H is saying is that the total enthalpy of the products per mole minus the total enthalpy of the reactants per mole is equal to minus 904 kilojoules. So in general, as a result of this reaction, minus 904 kilojoules per mole of energy in the form of enthalpy were released. If this was a constant pressure process, then you could say that this energy is heat, is in purely the form of heat. The per mole for the units of the enthalpy of the reaction, that's kind of confusing to me. So you might be confused as well. It's almost like it's saying that this is the normalized enthalpy of reaction. So if it's normalized, like, okay, when you have something per mass, like, or per kilogram, the density, let's say, well, that density doesn't change if you increase the amount of mass, right? Because it's normalized. So it almost makes it seem like, well, if we multiply this equation by 5, it's still the same amount of change in enthalpy per mole of reactant, per mole of product. But that's not the way it is. We know that from the video where we went through the textbook, and as we're going to see in the next problem, if we multiply this by 2, then delta H changes to, so that would be like minus 1808 kilojoules per mole. Okay, so what this is saying, the way you interpret this, and again, this might be counterintuitive to the way you interpret other quantities for other areas of science, for example, like density. This is saying, so if you have 4 moles of NH3 reacting with 5 moles of O2 to produce 4 moles of NO and 6 moles of H2O, then this much energy in the form of enthalpy is released. This many kilojoules. Not kilojoules per mole. I mean, you could say per mole, I guess, but this is kind of confusing to me. Okay, so like from a stoichiometry standpoint, the way you look at this is for every 4 moles of NH3 consumed, 904 kilojoules of enthalpy energy are released. For every 5 moles of O2 consumed, 904 kilojoules of enthalpy energy are released. Like, you look at this from the standpoint of the entire reaction as a unit. That's what this energy is being released. This entire reaction happening as a unit. but you don't look at it on like a per mole basis from the standpoint of like that it's normalized. And in later chapters, we're going to see why it's defined this way. So let's take a look at the next problem and you'll get a better sense of the idea of this. Consider this reaction, okay? What is the value of delta H if the equation is multiplied throughout by 2? All right, so we know that if we multiply an entire chemical equation by a constant, then you multiply the delta H or whatever, delta U, but here the delta H by that constant. So 2 times minus 1452.8 minus 2905.6. So and again, to me, this is kind of confusing because it's like saying if you've got an iron ball and it has this density, now you double the size of that iron ball. What's its density? It's the same density. It's volume per kilogram. So just because you double the size of the ball and you've increased the amount of kilograms and the volume, it doesn't matter. The density is the density. But that's not the way you look at energy changes of chemical reactions. If you multiply the entire chemical equation by a constant, then you multiply the delta H by that same constant. Okay, what is the value of delta H if the direction of the reaction is reversed so the products become the reactants and vice versa? When you do that, you just multiply the delta H or the energy change by minus 1. So this will be okay. Now here we're going to get a good sense of this kilojoules per mole idea. What is the value of delta H if water vapor instead of liquid water is formed as the product? Okay, so if we reference this table from the textbook, we see that the heat of vaporization, so H2O liquid to H2O gas, the delta H is 44 kilojoules per mole. Okay, so what they're saying is, what is the value of this delta H if this is a gas instead of a liquid? So we need to factor in this delta H is equal to 44 kilojoules per mole into the enthalpy calculation. So how do you calculate the enthalpy of a reaction? You say the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. Okay, right now this is equal to minus 1452.8 kilojoules per mole. Okay, so what we're changing is this sum here, we're adding this to it, right? We're incorporating the increase in enthalpy of the products due to going from H2O liquid to gas. Well, if you look at the units, we just need to add 44 here. So to maintain the equality, you just add 44 here. Because the units, kilojoules per mole, that's what's confusing to me. Because that's not what we're going to do. The reason why we're not going to do that is because, again, this is not, you don't think about this as normalized in the sense of how density is normalized per mass. Because, again, this is the amount of energy in terms of enthalpy released per, let's say, 4 moles of H2O produced. Not per 1 mole of H2O, per 4 moles. So the way we look at this is that this total reaction here, they want us to think about it as you have 4 moles of H2O liquid being converted to 4 moles of H2O gas. So in that case, we take 44 times 4, so 176. So we're going to add 176 here. And to maintain the equality, we add 176 here. So the new delta H minus 1276.8. Okay, and we're leaving this in units of per mole, kilojoules per mole. I know that's really confusing. To me, it's confusing. And we'll see in later chapters why it's done this way. In chapter 17, we'll see why. Why this is the standard convention. But just keep in mind, this definitely is pretty unconventional compared to what we do normally in physics, engineering, and science classes. This is not saying that for each mole of something consumed or produced, this many kilojoules of heat are released or enthalpy are released. If that was the case, then if we multiplied the entire equation by a constant, then the delta H in terms of per mole wouldn't change. But it does. So it's different. The first step in the industrial recovery of zinc from the zinc sulfide ore is roasting. That is the conversion of zinc sulfide to zinc oxide by heating. Here's the reaction. Calculate the heat evolved in kilojoules per gram of zinc sulfide roasted. Okay, so we know that the way we interpret this delta H, and we're looking at this zinc sulfide, is that so for every 879 kilojoules of enthalpy energy released, 2 moles of zinc sulfide were consumed. Okay, so now we just want to make this per gram. So we need to convert from moles of zinc sulfide to grams of zinc sulfide, we need the molar mass of zinc sulfide. Okay, atomic weight of zinc, 65.38. Atomic weight of sulfur, 32.06. So 97.44. Or no, that's no. Grams of zinc sulfide per mole of zinc sulfide. So for every 1 mole of zinc sulfide, there are 97.44 grams of zinc sulfide. And that's it, because they're asking us kilojoules per gram of zinc sulfide. Minus 4.51. Kilojoules per gram of zinc sulfide. Consider the reaction. If 2 moles of H2O gas are converted to H2 gas and O2 against a pressure of 1 atmosphere at 125 degrees Celsius, what is the delta U for this reaction? Okay, so we know that H is equal to U plus PV. I mean, we know that to get the internal energy, you just take the enthalpy and subtract out the PV work, because that's what enthalpy is. But just starting from the definition of enthalpy, if we now look at the change, so delta H, we say delta U, but we're at a constant pressure, so this is just P delta V. So delta U is equal to delta H minus P delta V. But we already knew this intuitively, because all enthalpy is just internal energy, and you're adding the P delta V work, or the pressure volume work done by the system on the surroundings, or vice versa. Here pressure is constant, so we just have P delta V. We've got delta H. This energy is supplied to the system. And so if delta V is negative, we want that to add here. And so that's why this minus sign's there. So how do we get P delta V work? Remember, we just look for gases in the reaction. Most of the time, the changes in volumes of liquids and solids is negligible, because that's it. That's all we're analyzing is the delta V of the system. That's it. Well, only any significant delta V's of the system are going to involve gases. And it's saying the pressure is constant, and it doesn't necessarily mean the temperature is constant, but you can see that That's state 1, we're at 1 atmosphere this temperature. State 2, we're at 1 atmosphere this temperature. We go from 2 moles of total gas to 3 moles of total gas. So, okay, how do we calculate the delta V from here to here? Well, we're going from state 1 of an ideal gas to state 2 of an ideal gas. So we can use like a P1, V1, T1 equals P2, V2, T2 type formula. So we say PV is equal to nRT. We start here. And going from state 1 to state 2, like for what we're doing here, we don't have to consider what's constant during the reaction. All we're looking at is in before and after, what's the same. Because the temperature isn't necessarily constant during the reaction, but as far as the two states we're comparing, the temperature is constant. So P is constant, T is constant. N is not constant, well, and R is constant, and then V is not constant. So let's put all of the constants on one side. P over RT is equal to N over V. Okay, so this is equal to a constant, which means that N1 over V1 is equal to N2 over V2. We know N1 is 2 moles. We know N2 is 3 moles. Okay, do we know V1? Yeah, we can calculate V1. So V1 is equal to N is 2, R is, let's just stick with liters for now. We'll convert later. So 0.082057, that's liter atmospheres per mole Kelvin. T is 125 plus 273, 398. nRT over P, 1. So this is going to be in liters. 2 times 0.082057 times 398. 65.3 liters. Okay, so what is V2? V2 is V1 N2 over N1. So 65.3 N2 is 3. Okay, so V2, well, okay, times 1.5. 98.0. Okay, so delta U is equal to, well, let's get P delta V first. So P is 1, and then delta V is, so V2 minus V1. So we take this minus this, 32.7. So 32.7 liter atmospheres. This is P delta V. Okay, but we need to convert this to kilojoules. So we've got 101.325 joules per liter atmosphere. Okay, and then there's 1,000 joules per kilojoule. So 32.7 times 101.325 divided by 3.31. So 3.31 kilojoules. So that's the P delta V work done. It's positive. The volume increased. So this is going to subtract from the enthalpy that was, this was the enthalpy that was added to the system. And so the P delta V work, since it was done on the surroundings, it's going to subtract from this. So delta U is equal to, the delta H is 483.6 minus 3.31. .3. That's the delta U for the reaction. Why didn't I put kilojoules per mole? I guess because I'm not writing this right next to a reaction. It's confusing. It's confusing how they use kilojoules per mole, like this. If I'm putting it next to a reaction, I'll put kilojoules per mole. But even if I did put this answer as kilojoules per mole, the context would still be there that I'm talking about this reaction. So I could put that and it would be okay. But the way that I see it in the chemistry textbook, it's like if it's right next to a reaction, they'll put the per mole. If it's kind of on its own, they'll just put energy. But again, I don't mean to beat a dead horse here, but this is really confusing. It can be really confusing. This is not really saying, this is not like a normalized per mole, right? If you think about this as normalized, then you could do 100 moles of H2O gas to start. And this would still just be 483.6 kilojoules per mole. But that's not the way it is. That's not the way they use this here. And we'll see why in later chapters. So this is really kind of just saying kilojoules. It's really just saying just energy. I know it's confusing, but this is something you're just going to have to memorize when it comes to statements of energy changes in chemical reactions. Consider this reaction. If 3 moles of H2 react with 3 moles of Cl2 to form HCl, calculate the work done in joules against a pressure of 1 atmosphere at 25 degrees Celsius. What is delta U for this reaction? Assume the reaction goes to completion. Okay, so one thing I noticed is that we have 1 mole of gas here, 1 mole of gas here, so that's 2 moles of gas. And the products, we also have 2 moles of gas. We know that if the pressure is the same and the temperature is the same, and this isn't necessarily a constant temperature process, but at least the reactants and the products are at the same temperature. So going from state 1 to state 2, it's the same pressure. We know that if we have 2 ideal gases and they're at the same pressure and temperature, then their volumes are proportional to the number of moles of gas. Well, the number of moles of gas is the same. 2 moles here, 2 moles here. So the delta V is going to be 0. What does that mean? That means that delta U is equal to delta H. P delta V here is 0. That's why. Because delta H is just the internal energy plus the pressure volume work. Well, there is no pressure volume work. So the work done is 0. And delta U is just this. This is delta U. It's a constant volume process, right? Because the delta V is 0. And what do we know about a constant volume process? This is both constant volume and constant pressure. That's why delta U is equal to delta H, which is equal to the heat transferred. Because this is QP and QV. This is QP because this is both constant pressure and constant volume. So delta U is equal to minus 184.6 kilojoules per mole. Or, well, no, I'm going to put kilojoules. I'm not going to put per mole because it's not right next to the reaction. But like if I was doing, I could do this. I could say delta U, and that would be fine. It's right next to the reaction, so you know what that means. That's really confusing. You're going to have to, I apologize for you having to sort of memorize this, how this is not, this does not mean normalized in the same way that density is normalized per kilogram. You literally read the equation as it is stated. 1 mole of H2 reacts with 1 mole of Cl2 to produce 2 moles of HCl. When that exact thing happens, this many kilojoules of energy are released in the form of enthalpy. If it said 2 moles of H2 react with 2 moles of CO2 to produce 4 moles of HCl, you would say that this times 2 kilojoules of energy in the form of enthalpy are released.